So we're going to use this band limited stuff to try and build a discrete version of general covariance, right? And we're going to try and use it to do all the same things we did with the continuous general covariance. And I hope from like our ability to resample, you can see the analogy I'm building up to, right? So what we've done so far is we started with a band limited function and we induced different discrete representations of it. But now let's add physics by adding in some dynamics, and we're going to reverse the picture. We're going to start with a lattice formulation and then build from it a band limited formulation. So let's pretend momentarily that we take our lattice formulations of our theories very seriously, and we believe that they are, you know, the fundamental thing. And then let's see if we can dissuade ourselves from believing that, basically. And here's the proposed analogy once again. Coordinate systems are like lattice structure, right? We can always change coordinates, and just like that, we can always do our Shannon-Nyquist resampling and choose different lattice points to represent our theory, right? And there's a formulation which is coordinate independent, which is a generally covariant formulation, right? And just like this, there's a lattice structure independent formulation, which is the band limited formulation. So that's basically how the analogy is going to work. But it pays a lot to go see it in detail through a few examples. So let's consider the 1D nearest neighbor heat equation here. So we have the time derivative equals something like the space derivative squared. But since we're on a lattice, we can't exactly write that down. So here's the nearest neighbor second derivative approximation. Or equivalently, we can collect all of these values of the heat field together into a big vector, right? And then this is a linear equation on them. And so the time derivative of this vector is alpha over a squared. And then this delta is just the collection of ones and minus twos and ones, which reproduces 19. So it's a tridiagonal matrix with 1, minus 2, 1. Okay, so let's think about this. What can we do? Let's say we really, really believe that there's a lattice structure underlying our universe, and that the values of the field at those places evolves by this equation, right? What we could do is take those discrete values and imagine them as being samples drawn from some band limited function, psi b, right? So psi b evaluated at xn, for x is na. You can think of that as, you imagine that your sample came from, or your value came from sampling this distribution at that place. We can use these samples to reconstruct psi b exactly. So just knowing it at these places, we can reconstruct psi b everywhere by some sort of a sync reconstruction. So now we've moved the state of the system from some discrete thing into this band limited representation. So in addition to moving the state of the world at each time into the band limited setting, you can also move the dynamics. Let's take the derivative of this band limited thing, and you can push that through to be in terms of the derivative of all these discrete values here, right? And do some work, which I've hidden here. And you find out that this psi b, it does evolve by a nice differential equation, or nice in quotes maybe. It evolves by this differential equation here with this nasty cosh of a derivative thing. And the complicated cosh term is the continuum, or I should say band limited analog of this nearest neighbor derivative. All right, and the way this cosh comes up is we have a shift of one lattice site to the right, right? If you do the Taylor expansion of this, you'll find that you can rewrite it in this form here, so that the exponential of the derivative is a translation, right? And so this cosh is one translation to the right and one translation to the left, and that's why cosh shows up. Anyway, and if you expand this cosh thing as a function, as a series in A, you see that up to first order, or at lowest order, it's just the derivative squared, right? So this would give back the continuum heat equation, but then we have these other terms coming on here. Okay, let's call that H1, that whole theory, 1 for nearest neighbor, right? So we had this this discrete version, and then we found this was the differential equation that the band limited function obeyed. So we can make up H2, which is the second to nearest neighbor approximation for the second derivative. So you look at not only your neighbors, but their neighbors, and from those 5 points, including yourself, construct the best second derivative you can. it turns out that H2, the reconstruction in this case, obeys a different differential equation, this one here. And then H3 will take the limit on n going to infinity. So let's do an infinite range derivative approximation here. And it turns out in this case, the band limited thing just obeys something with just the second derivative squared. No higher derivatives show up in this particular example H3. Okay, so we've got all these different types of dynamics, all these different heat equations, which have each of them a discrete version and a band limited version. Let's think a little bit about how those work. These are really different theories, these three things. So in each case, the eigensolutions of these differential equations in each case are plane waves with some frequencies k less than capital K. Right? And those plane waves decay exponentially in time. If you're familiar with the heat equation at all, you know that sines and cosines decay exponentially in time at a rate proportional to the square of their wave number. Right? And so in this case, you find for H1, you have like a modified heat decay rate. In H2, you have a different one. In H3, you have something that matches the continuum decay rate up until the band limit here, and then it stops, because these band limited theories, they only exist for wave numbers up to k, capital K. Right? And so they abruptly stop at this point, whereas the continuum, of course, includes all wave numbers out to infinity. But below that bandwidth, there's no difference between H3 and the continuum theory. So here's the first lesson for us. There's no reason that the lattice theory needs to have any different dynamics than your continuum theory, at least not if you restrict everything to be below the bandwidth K. So oftentimes you'll hear people think that, oh, when we put things on a lattice, we have to make some, we have to make some modification to the dynamics to make it all fit. That's just not true. You can mathematically formulate a lattice equation which has the same dynamics, at least below the bandwidth. Okay, so what we can do is let's plot these discrete values psi n of t as these dashed lines here, and you can also plot the band limited function here in a space-time diagram. Right, so here's space and here's time. Now this isn't the Lorentzian theory, but we can still put it in space-time, because why not? Now what we can do is at each time, we can pick new sample points. Right, and so for instance, we might pick these red sample points at each time, and they move around, and they don't have to stay uniformly spaced, although they do here. And what we can do is we sample the field on these new sample values, and then those discrete values you would find in that case would obey some other equation. Maybe not the same one as the old one. In most times, they won't obey the same equation that the old lattice points did, but they are completely sufficient to represent the dynamics. You can totally do this, and that's fine. But what if we choose this particular resampling where we just shift everything a little bit over, right? So would the shifted red sample points obey the same equations that the original dashed sample points did? And it turns out that they do, if you work that out. So the second lesson here, what this shows essentially is that even though our theory was at first written in terms of a discrete lattice, there's no reason it can't have a continuous symmetry. The fact that the red sample points and the black sample points obey the same equation shows that we have a continuous translation symmetry here. But maybe that's a little bit hard to see. There's an easier way to see it, or a more interesting way to see it, I think, in terms of a rotation symmetry. So consider this initial condition for the 2D heat equation that we've been talking about, right? So we can sample this initial condition on this square lattice, let's say, and then we can then evolve it by our dynamics in, let's say, one of two ways. So let's make up a new heat equation H4, which is this nearest neighbor derivative in the x direction and the nearest neighbor derivative in the y direction. And then H5 is these two infinite range derivatives in the x and y directions. Right? So we can take this initial sampling, and then we can evolve it either by H4 or we can evolve it by H5. And those would yield different values at different times in the future because the dynamics are different. Right? And in each of these cases, we can do a reconstruction back to the band limited function at the end of that. And in this first case where we did H4, we see that the state's no longer rotation invariant. We've got these spikes coming off the sides and bottom here. Whereas in the H5 case, it remains rotation invariant at the end of the day. And so side by side, what we did, same initial condition, same initial sampling. We evolved by two different types of dynamics, and then we do the reconstruction. And the dynamics in some cases ends up rotation invariant, in some cases it doesn't, right? And so this shows the same thing as lesson 2 from before, but now with rotation invariance. So we can have rotation invariant dynamics described in terms of a square lattice. No problem at all, right? And moreover, we could take this initial condition here and then sample it on a hexagonal lattice or on an irregular lattice and evolve those forward in time by this lattice's version of H5, you know? It's still exactly H5, the same dynamics, just rewritten in terms of these sample points. And in each case, you'll find that the state's rotation invariant at the end of the day. Right, so you can have rotation invariant dynamics described in terms of any lattice that you like. So that's not a problem for us. Right. And here's another couple comparisons. So in this case, we have this initial condition here. We do an initial sampling of it on either a square lattice or a hexagonal lattice. And then we evolve by H4, which is the one that wasn't rotation invariant, and do a reconstruction. And we find the same thing in both cases at the end of the day. So the fact that H4 has a fourfold symmetry to its dynamics has nothing to do with the fact that it was represented with on square lattice. Right? I can represent exactly that same dynamics with exactly its same asymmetries with a hexagonal lattice. So what this shows ultimately is that the dynamics of your lattice theory is the symmetries of that is just the symmetries of the dynamics. It has nothing to do with the symmetries of the lattice at all. And this really motivates me to think about the analogy that I'm trying to make. Because think about, I write down my theory in some continuous coordinate system, right? There's no reason that the symmetries of my theory have to match in any way the symmetries of the coordinates I used to write it down. There's just no reason for that, right? The symmetries are of the dynamics itself, independent of any coordinate representation. Just like the symmetries here are independent of any lattice that you choose to represent your thing with. Okay, so let's now put together this idea of having a band-limited representation of something with also having a generally covariant representation of it. So we'll go through this a little bit quickly, maybe, but this discrete 2D heat equation here that I write down in terms of these discrete values relating to each other in some way over time. It has a band-limited representation like this, which I hope you're not surprised about. These dBs just turned into derivatives in the band-limited one. Remember, this is the infinite range derivative that we were talking about earlier. So we take this discrete equation and we give it a band-limited representation, which now references no lattice structure in particular. We could put this on a different lattice. We could put 29 on a hexagonal lattice, and it would come out something like 28, but with different operators here, right? And we can further reformulate 29 in a generally covariant way. Like I showed you how to write down the heat equation in a generally covariant way before. Now let's do that same thing. We have here a manifold, a metric in time, a metric in space, a derivative, and a time-like vector field, and then psi just gets a subscript b here. And the dynamical equations for this are just the same as before, except with these subscript b's on them. Okay, so let's compare H5 written in this band-limited and generally covariant way with the continuum heat equation. I look closely at the two. What is the difference? The only difference here is that psi b is band-limited, whereas psi is unrestricted. So the only bit of structure that having a discrete theory has put on us is a restriction on the matter field. It hasn't introduced any new geometric objects in the background of our theory, just a restriction on the field in this case, right? And since these dynamics actually, if you look at the continuum heat equation, it preserves band limits. Like plane wave solutions evolve to plane wave solutions, right? And so ultimately, this just amounts to a restriction of the initial condition. If I have a continuum heat equation plus a restriction that the initial condition is band limited, and that's equivalent to H5, right? And then I discretize my theory just by putting an extra condition on my initial condition. Right. Let's go through the same rigmarole with the Klein-Gordon equation. So here's the discrete 2D Klein-Gordon equation with these infinite range derivatives here, or infinite range derivative approximations, you might want to call them. Anyway, you can give this a band limited representation here, and then you can give it a generally covariant representation like this. And just as before, compare this with the continuum Klein-Gordon equation right in here. So this is SR1 from before. So we have a manifold, a metric, and a field, manifold, metric, field, same differential equations, just with the B subscript. Right. The only difference is that the field is band limited, whereas in the second case, it's unrestricted. And since, again, the Klein-Gordon equation preserves band limits as you move forward in time, this is just a restriction on the initial condition. So, so really, having a lattice description of our theory in these two cases has been nothing except putting a restriction on the initial condition. And let me put this in really plain terms, or really striking terms, let's say. This discrete 2D Klein-Gordon equation here, these particular discrete values relating to each other over time in this way, this equation here has a full Poincare symmetry group. There's no reason that this discretized object can't be Poincare, have a Poincare symmetry, right? Even though there's like continuous translations and boosts and all of that inside of here. With one slight exception, I should note that in this Lorentzian type theories, the bandwidth kind of has a frame dependent value. So the bandwidth K, it depends on which flat space-like hypersurface you compute it on. There's a way of formalizing what this means that I can talk more about later. But depending on how you pick the surface you compute this on, its value changes. But the fact that it's finite doesn't change. And you can think of this as just length contraction, shrinking lengths, and then expanding bandwidths, essentially. Right. So what I've tried to argue here is that, what I think I've successfully argued is that we have this analogy that coordinate systems are the same as lattice structure or analogous to, right? Changing coordinates is just like Shannon-Nyquist resampling, and generally covariant formulation is just like a band limited formulation. I think this carries over fairly well. And then once we've given our lattice theory a band limited reformulation, we can then give it a generally covariant reformulation as well. And so what has all this shown us? We've seen that the lattice structure underlying a lattice theory has the same level of physical import as coordinates do, which is none at all, right? Like the lattice underlying your theory should not be seen as part of like the material content of your theory. It's not there. It's a representational artifact in the same way coordinates are. Nothing can depend on them, right? And the symmetries of your theory, like I mentioned, are the symmetries of the dynamics, not of the lattice you represent it on. Okay, but let me go through the conclusions in order because I'm skipping ahead. Okay. Introducing the lattice to the continuum theory doesn't need us to distort the dynamics much, if at all. No distorted heat rate decays, no distorted, what are they called? Dispersion relations, right? If you did that to the Klein-Gordon equation. In the two examples we've seen, the lattice does as little as restrict the allowed initial conditions. And this changes a little bit for nonlinear theories, which I have an example of in sort of the after slides to the talk. But still, it's mostly the same-ish. And in particular, yeah, the lattice doesn't need to cause modified heat decay rates or modified dispersion relations. It doesn't need to change the dynamics at all, besides cutting out high-frequency stuff. That's all that the lattice representation forces you into believing. And the second point is that the lattice doesn't restrict in any way the symmetries that our theory can have, right? The symmetries of our dynamic is completely independent of the symmetries of a given lattice structure. In particular, I've showed that we can have a fourfold rotation symmetry on a hexagonal lattice. We can have continuous rotation symmetry on an irregular lattice. We'd have Poincare invariant dynamics on a square lattice. Basically, any symmetry fits on any lattice. There's no reason that the lattice has to force your hand in terms of symmetry in one way or the other. Right. So this, I'll hear the questions this raises for you, but this raises some questions for me, which I'd like to just put out there. We can talk about them in a moment. What would it be like if the world really had a certain lattice underpinning it? I mean, given all this discussion, could that ever be experimentally established? If I believe the world has a square lattice and you believe it has a hexagonal lattice, right? I can write down an equation which explains everything. You can write down an equation which explains everything. I don't see how we would pick between those two experimentally, besides maybe on terms of elegance or something. But if we're really going for elegance, then the band limited formulation is the most elegant, in the same way that generally covariant formulations are the most elegant. I would think if you got really deep into fighting about if the world has a square or a hexagonal representation, the lattice underlying it, really, you would end up agreeing that there's no such structure in the world as a lattice theory. It's something we impose on it, to pick up a representation. Anyway, a puzzle that arises with this is what's local in the lattice formulation in terms of nearest neighbors is non-local in terms of the band-limited formulation. It involves all these really high derivatives. And likewise, what's local in the band-limited formulation, which is just the derivative, is non-local in terms of the lattice formulation. It has an infinite range derivative associated with it. So if we want our theories to be local, which of these notions of locality should we demand our theory has? Which one should we prefer? A partial answer to this, I think, is that we saw that maximizing our symmetries in our future theories, which we might be wanting to do, sort of breaks this and tells us that the band-limited formulation is the one we should go with. And so it's the locality of that formulation that we should probably be caring about. But I'm open to other perspectives on that. And then the last thing this raises for me is what's the possibility for giving us a band-limited theory of gravity, like a band-limited Newton-Cartan theory? I've been trying to write that down, and I have some progress on it, but I don't know. I can show you later. And what about a band-limited and background-independent theory? There's all those questions about what background independence mean, right? But does this go any way to helping us establish what a discrete version of background independence might be? And then can we write down some band-limited version of GR? That would be interesting to know. All right, so thank you for your attention. I'll take any questions now.
Very nice, Dan. Good,
yeah.
Really good, really nice. There's something that, I mean, all that you said makes total sense, 100%. So it's very easy to get on board. There are some problems, though, that I find when I try to apply to what we know of GR and things like that, when I try to make it, to make sense of it in terms of GR. Because it makes total sense if you, if you already have a lattice, for example, if there's something physical that you call a lattice, in mind that I have, I don't know, a crystal or whatever, some structure of things that are coupled that are really in a lattice. I can totally see how it's so cool to represent it, in the band-limited picture. And it's kind of cool and everything checks up, and you can say, okay, which one is the best mathematical description? Well, there are reasons for both, right? If it's a real lattice that exists, or maybe you want to talk about the elements of reality and talk about the lattice. But maybe if you say well, I mean, there might not be a lattice in there. Maybe what there is the band. Maybe the real thing is the band-limited nature of the theory, right?
Right.
What does that mean? Yeah, it makes more sense in the sense that it's easier. So something that doesn't make sense to me is in a theory like GR to establish a lattice structure, because then you have to privilege something, right? I mean, you have to privilege some frame, for example, to establish a lattice structure. No,
you don't. I don't think so.
Hold on. For a lattice structure, if you wanted to have a lattice structure, you need to privilege some frame in one sense or another.
I don't think so. No, you don't.
Okay.
Sorry. Would you say the same thing about special relativity?
I would say the same thing about special relativity. Yes.
Okay. Here I've written down this theory here about these discrete points is special relativity with a band limit, right?
Yeah. With a band limit,
it takes out no frame. I don't know what you mean.
All that I mean. Imagine that there's an underlying lattice. That's what I mean. Imagine that.
Oh, if there really is one, sure.
That's right.
Okay.
So I was actually defending your approach, not attacking.
Okay.
In the sense that it makes no sense to think of a physical lattice describing GR or special relativity, not much more sense, but it does make sense a lot to talk about band-limited functions and band-limited representation of the dynamics.
Right.
But I still have troubles to translate this into physics, in the sense that, so imagine that there is a band-limited theory that is generally covariant, and imagine that there's a band-limited theory that you want to say, no, that's the real GR. That's what GR really, right? GR is some effective theory that comes out of this fundamental other one that is band-limited. What is the physics? What are the degrees of freedom in that theory? Because again, as you said, locality is a bit of an issue here, right? I want to be able to define local observables in any theory that I want. Imagine that I want to have, I don't know, I want to have access to measuring the amplitude of a Klein-Gordon field around here, for example, right? Sure. If you introduce a band-limited description, then your derivatives are very, very non-local in what we call the emergent space, right? And then your lab has to live almost everywhere to be able to do experiments. So how is that? How do you make sense of this?
Yeah, I don't know. Like, this raises a lot of questions about locality because, like I mentioned before, band-limited functions can't be compactly supported in space, right? And like to exclude things like that by fiat, like everything must exist everywhere. Like everything's going to be spread out.
That's right.
I can't compactify or localize anything.
But experiments are local. So that's my issue. You make an experiment
right
here. What am I sampling? If I really am doing an experiment here in my room, what am I sampling? You see what I mean? Like,
yeah, no, that's a great question. I mean, the questions about locality that come up from this are probably the most interesting because I don't know if you really believe that things are local in sort of like a compactly supported box function sort of way, right? Then you have to believe in super high, super high wave numbers.
Right.
In reality, like you just need them, and so I would one philosophy project I would think about this is what harm does that do you, say, in terms of counterfactuals? Like if I would like to say, oh, the world evolved this way, but if the world had been different just in this compactly supported region, things would have evolved a different way, right? I can't make sense of that counterfactual in terms of a band-limited theory. If I want to change the field in one place, I have to change it everywhere.
That's right. Yeah.
So it does a lot of harm to your metaphysics to do that. But can you? But also, it seems unreasonable that in practice, if I just want to do actual practical counterfactuals, like, oh, if it had rained that day, if there hadn't been a cloud over London, then this would have happened, right? Like, why, when I'm making sense of what exactly that means, if there hadn't been a cloud over London, like, do I really have to believe in arbitrarily high wave numbers to make sense of that? Like it seems as a matter of practice that I don't. Like I talk about the clouds over London all the time, and like, why do I have to buy into a specific sort of ultraviolet structure to make sense of that? Like I don't know. I feel like there should be a way to make counterfactuals just in everyday life that is sort of independent of the UV structure of the world.
My main problem is localization, because localization is just tricky. And the thing is that I assume if you want to postulate that localization should be possible, you know what I mean? In the sense that I should be able to do local experiments. I may be wrong here, maybe it's impossible, but I'm assuming that I should be able to do local experiments because my life is finite. I only cover a small region of space-time during my life. And then everything that is knowable to me through experiments is things that are localized, right? And I do have trouble with, go ahead.
Right. Let me just say that the dynamics of like this Klein-Gordon equation, this band-limited one, this is local. Like in the band-limited picture.
In the
dynamics is local. Just the issue is that you can't have physical objects, which are local.
That's right.
But the dynamics itself.
No, I agree.
A little bit in the future evolves just because of
the dynamic is causal and local and everything. So given if you were to really have something localized, it would propagate in the way that we expect localized things to propagate. But the problem is that you don't have those local objects to work with, right?
They just can't exist.
That's right.
But so I don't know, like the dynamics of the theory is all local and causal and everything you'd want. It's just that the types of experimental apparatuses that you want to build just can't be built.
Yes, that's the.
Oh well, like.
So that's my only issue with it, and the issue is not that. It's actually how do we make sense. So the issue is not that this theory cannot be right because it precludes those things from existing. It's actually that maybe what this needs is a way to make sense of your measurement apparatuses, you know, in this context. How do you make sense? How do the measurements apparatus that we see and we use emerge out of a band-limited theory? Right? I mean, that would be the way to maybe think about it.
No, yeah, that's a question I'd like to look into, because like grounding this in terms of measurement and locality and all that, that's a great
That is something that on a different notion I'm also looking at with Thales. So maybe that's something we can discuss at some point, because using different approaches, I'm looking at definitely not band-limited theory and things like this, but I'm looking at, I think they might be even related. I'm looking at, so with Thales, I'm doing a project in which it's so sad that Thales left, in which I'm looking at in the physics of space-time out of just outcome of local measurements, local detectors that do local measurements. Right. To the point that I want in the end to do away with the background structure and just describe the physics of gravity through outcome of measurements. Maybe we can talk about that at some point, because it might be, I think it might be, there are some points of relation in between these things, because certainly detectors are band-limited objects, you know what I mean?
Right. Yeah, they're certainly very insensitive to the UV.
That's right. That's right. And yet, I think that it is possible to talk about emergent gravity and emergent space-time out of just, it might not what we're real, it might not in all that I might not have a theory that has gravity with quantum field living in it, and I can make measurements on them in the usual way we make measurements of fields. And then you say, well, in the end, imagine that I now do away with the background, do away with the field, do away with space-time, and all that I have is the outcome of those measurements. Can I reformulate the whole thing? Can I reformulate the causal relationships between the points in what was the points in space-time, just in terms of the outcome of measurements? And those outcomes of measurements are band-limited, are in nature band-limited. Right. And there's a lot of evidence telling me that I can.
Right, but I mean, you can't have a band-limited detector also be, you know, compactly supported in space. I mean,
that is correct.
To put this in terms of your ear, I mean, we were talking about you listen to a song, and you only have a band-limited auditory range, right?
Yeah.
Okay, so there's that. But also, when I listened to the song, I only heard frequencies in this range, sure, but I also only listened to the song for 10 minutes.
That's correct.
Which one is it? It cannot be both.
Like, I think the secret is in the tails. As in, like, the way to reconcile the two is in the way the tails interact. There are a subset of functions, and in terms of resolution and uncertainties. Because certainly it's true that our hearing is band-limited. And also it is true that songs last for a finite amount of time.
Right.
How is that reconciled? You see what I mean?
Yeah, well, it's also like, you can't reconcile those two unless you admit that there's also like a finite sensitivity to the different responses, right?
Exactly right. And that's
if you make enough buzz there, you can fit both in, and you can be.
That's right. And it's the noise. I think what saves us is the noise, and what saves us is that noise may be actually a fundamental thing in nature. You see what I mean?
That's possible, I guess.
That is exactly the way I want to take it. I want to check if it works that way, because there will be certainly some sensitivity issues when you describe things in terms of outcomes of detectors. And those sensitivity issues, you blur the response of the detector, and those sensitivity issues reconcile the fact that you can have band-limited things and also finite in nature. It's not in a way of compact support, but in a way of like tails that you stop trusting, because you know what I mean? The signal-to-noise ratio is critically low in the regions of the tails.
Right, right.
Kind of like that.
Yeah, that makes sense to me, yeah.
Anyway, we should talk more about that. I need to go soon because I have somebody waiting for me for the next meeting. This was an amazing talk.
Yeah.
I really like that thing that you're doing, Ben. I think there's a lot of future in doing this.
No, I think it's very interesting. I mean, any other questions from the students, I guess?
Yeah, I had a small question.
Yeah.
I really liked the presentation also. It's amazing.
Thank you.
And it was about the bandwidth. You said that if you put it in a general relativity context, you can, well, or special relativity, I guess, you can get like contraction and the bandwidth can change.
Right.
But can it change like until it becomes like infinitesimal, like really small?
It stays finite. If you tell me in one frame it has a value k, then it has to. It can be arbitrarily small if I do an arbitrarily large boost. Wait, no, sorry, it can't be arbitrarily small. No, there's a minimum value it would have. Sorry, there's going to be like a finite minimum it could have. If you boost too far one way, it starts increasing. If you boost too far the other way, it starts increasing again. So there's some intermediate frame where it just so happens that this particular matter distribution has the lowest bandwidth in that particular frame.
Oh, that's cool.
Just like we're moving with respect to the CMB, right? There's some frame in which the CMB velocity is minimized. There just happens to be like the way the matter is. There's just one that's most co-moving with it, right? Same thing happens here. There's one frame that has the minimum bandwidth.
Okay.
Yeah.
Thanks.
So I have a question about this idea between the actual existence of a physical lattice and the way that you can get away with it with the formulation in terms of band limited functions. So if you talk about crystallography, for example, there you have a very concrete example of a theory in which there is a lattice and that has physical implications to what you actually observe in terms of, I don't know, scattering and like X-ray scattering and stuff like this. So how does that relate to this? What actual additional structure am I adding in that setup to say that there is some physical reality to the lattice, as opposed to, for example, if I do loop quantum gravity and the lattice is just a lattice structure that I can mess up with?
Right. Well, we believe like think about graphene or something, which is a hexagonal lattice. You know, it's a 2D hexagonal lattice, which I showed one of here. We believe that there is, you know, the structure of smaller length scales than the lattice spacing, because like we've split atoms and we've looked inside and like so those theories, the lattice definitely, there are lattices which physically exist in the world. I'm not saying none of them are real, but those lattices are the physical contents of the universe arranged in a lattice-like way, right? There can't be what I'm claiming is there can't be a lattice underneath that, if that makes sense. Like there can't be a lattice structure to space-time, because you would realize it's just an artifact of representation, is what I'm saying. But you can definitely have physical content arranged in a lattice-like way. Does that make sense?
I think so. Yeah.
Right. Oh, go ahead, Jose. I need to go soon. And when I go, even if Bruno is co-host, I'm gonna kick you out because I will start a meeting with my identifier. I've already tested it.
Okay.
So one last question, Jose, very brief, please.
Okay, yeah, no, it's. I was going to ask that I have some difficulties in making sense of what you mean by lattice structures having continuum symmetries, because here I see that you change the lattices and so on, but every time you are formulating this, there is some continuum space underneath. I mean, you are changing the lattice, but you are always in R2. So if the lattice is physical, then there is no continuum space underneath, and I don't know how this would be formulated.
No, yeah, you're right. And I have a write-up of this whole thing, which I can send to you guys once it's a bit more polished. But I deal with that there a bit, right? I think I'm only dealing with theories where there is some continuous manifold, and then the points are embedded on it somehow. But then you already have this continuous theory space below it. But I'm not exactly sure about that. Like, if I'm given a discrete system, I can sort of make up whatever manifold I think fits under it. So I'm a little bit unclear about that myself.
Yeah, but that's the point. You can't ban the existence of lattices if you are always relying on the existence of an underlying manifold. And if on the other hand, if there is actually a physical lattice, then what you have to check is, I think the other way around, is like you have to check if any manifold you make up to fit that lattice actually gives you the same band limited representation, right? Or something like that. I don't know.
Yeah. I definitely want to think about that more, but that's a great question. Yeah. Okay, well, let's stop this so Eduardo can go. But if you guys want to keep talking about it, I'd be happy to start another Zoom call.
Yeah, this is very interesting stuff, Dan, though. I mean, it's amazing. I loved it.
Yeah, I'm planning to publish it at some point soon. So.
All right.
Okay.
Okay, guys, see you.